Hello everyone, welcome back. In this video, we're going to talk about gauge and absolute pressure, how to find them, and what the difference is. Now, what we're talking about is pressure at depth. In other words, pressure under the surface of a liquid, which is typically going to be water, and that is what I'm going to mostly be using for this video. To start out, let's have our water line. So this is the water surface here. Let's say at the bottom, like we're in a pool, this represents an area at the bottom of the pool on the floor. Now, above that surface, that particular area, we have a column of water. So think of it just like a big block of water. Since water has mass, it's basically a big block of a substance that is pressing down on the bottom of the pool, just like you would a wooden block or a steel block or a brick. Now, this column is going to have dimensions: length, width, height. So here's some basic geometry we already know. Length times width will give you area, and length times width times height will give you volume. So I'm going to put that here. Volume equals length times width times height. Next, we're going to take our density formula down here, and we're going to take it and rearrange it for mass, which simply gives us mass equals density times volume. That also means it would therefore equal density times length times width times height. Now, what we're really after is this: force earth on water. In other words, if someone sat on you, the amount of force that would be exerted on your chest would be equal to that person's weight. In other words, force earth on that person. The same exact thing is true here. The amount of force exerted on the floor of the pool in that area right down there would be equal to the weight of the water column, which would be mg, where g of course is 9.8 newtons per kilogram downward. So we therefore have mass, which we already derived as density, length times width times height, times g. In other words, density times volume times g. Okay, next up, let's take a look at pressure. So pressure, we have force over area. Force, as we just said, is force earth of the water column on the bottom of the pool, rho length width height times g, over area. Now, area, as we stated earlier, is length times width of this rectangle here. So we have length times width in the denominator. And of course, what happens here is these two things cancel. That means the pressure on this area on the bottom of the pool is equal to the density times the height of the water column times g. This equation is typically written as rho g h. This, by the way, is gauge pressure, and I'll explain the difference in a moment. For right now, a much more important thing needs to be stated, and it goes back to what I said in my last video, is that pressure in a fluid is exerted in all directions. So as a quick recap, in my last video I had this box, and this box is floating somewhere in the middle of the pool where the floor is down here somewhere. The water does not just exert a force downward on the box. There is a force on each side of the box that is touching the water. In other words, the water is exerting a force on all sides of this box. Down, up, left, right, forward, back, all sides. And if you notice, this arrow is slightly larger. The reason for that is this h. If I was to calculate the pressure to the top of the box, I would have a certain height 1. If I was to calculate the pressure at the bottom of the box, I would have height 2. Because height 2 is greater than height 1, therefore the pressure on the bottom of the box is greater. I know I keep restating this, but it's so important it bears repeating. So here's you. Once again, that means your head would be under less pressure than your feet if you were floating here underneath the surface of the water. So let's take one and let's do a quick one for real, just because some people like to see the math. All right, so we have our water column, base, width, height. Now, if I want the pressure at the bottom here, the length and width do not matter, because looking at our calculation here, the length and width cancels. In other words, pressure is per unit area, so it doesn't matter how big the area is. They're always going to cancel when using this derivation. So I have my pressure at depth formula. We'll use water, which is right down here, 1,000 kilograms per meter cubed, G, 9.8 units per kilogram, and a height of 8 meters. So looking at our units here, these 2 kilograms cancels. This meters cancels with one of these meters, so now I have meters squared, which leaves us newtons over meters squared, which is pressure. Therefore, we have 78,400 newtons per meter squared, or pascals, at 8 meters. For you imperial folk, that would be about 26 feet deep and 11.4 pounds per square inch. And as a reminder, that is the pressure in all directions exerted by the fluid that you would be in. And now let's talk about the actual difference between gauge and absolute pressure. So what we just did was gauge pressure. Here's what that means. That means that is the pressure at depth relative to the pressure at the water's surface. Because the truth is, you are under pressure right now. If you go outside and look up, there is a whole column of air above you. And air in physics is basically a fluid. In other words, air has a density. Therefore, it has a mass. All those air particles, oxygen, nitrogen, CO2, water vapor, etc., they all have mass and they all add up. And there is a large column of air above you exerting pressure on your head and all other parts of your body at all times. Gauge pressure essentially ignores that. That means gauge pressure is pressure at depth relative to the surface. It basically pretends that the surface pressure is zero. Not true, but again, it's a relative value. Absolute pressure does not do that. Absolute pressure is the absolute pressure from zero. Zero, zero. No pressure whatsoever. Think space, all right? Way out in space, no air particles or water particles or any other particles to exert a force on an object. Therefore, there's no pressure on that surface. So, what does that mean? Well, first, we have to talk about the pressure exerted on you right now, assuming you were standing or sitting on the surface of the Earth. In standard empirical terms, the pressure at the Earth's surface is known as 1 atmosphere. Basically, it's the pressure we feel all the time, so someone simply made it 1. Now, what does that mean in terms of pascals? Well, it means this. 1 atmosphere is equivalent to 101,325 pascals. Now, this may be the actual value, but we are not going to use that, mostly because the AP exam does not use that. In fact, a lot of places round this to 101,300, but we're going to round it even more. We are simply going to say it's 100,000, or 1 times 10 to the 5th pascals. It's going to make the math a lot easier. Now, how you get absolute value is actually quite simple once you know gauge pressure. Absolute pressure is rho g h plus the atmospheric pressure, which may be written as pressure ATM, but is more typically simply written as pressure naught. And this is nearly always assuming that pressure naught is pressure at sea level on the Earth, which is approximately 100,000 pascals. So to get absolute pressure, all you need to do is do gauge pressure and add this number. That's it. And once again, since this height is here, you will still have more pressure at your feet than your head because your feet are at a greater depth. Things you need to watch out for this are, it's very common to be asked, by what factor will the pressure change if you say double the depth or height to the waterline? Well, if you're talking gauge pressure and you double the depth, then the pressure is simply doubled. Rho GH, it's a direct relationship. However, in the absolute equation, it is not a direct relationship. So you would literally have to calculate both values and then do a comparison. Just to show you real quick, let's say we go down to 4 meters. At 4 meters, the gauge pressure would be 39,200 pascals. Now, if we were talking absolute pressure, you would have to add on the atmospheric, which would make this 139,200 pascals. Now, let's say I doubled this depth. This is the depth we were at earlier 8 meters, which we know is 78,400 pascals. The pressure at the new depth divided by the pressure at the old depth is, of course, 2. So we get a 2 times multiplier if you go double the depth, if you're talking gauge pressure. Now, if you're talking absolute pressure, then the new pressure is 178,400 pascals. That value divided by our original value will give us a multiplier of about 1.28 times. So gauge pressure would double because it's relative to the surface. But since absolute pressure includes the atmospheric pressure at the surface, it does not double. So you can't do a direct proportional reasoning method, which is saying if the depth doubles, then the pressure doubles. That's only for gauge pressure. Now, all this being said, you will mostly be dealing with gauge pressure in this course. Absolute pressure will come up most of the time when whoever is assessing you wants to see if you know what it is and if you can find it. And the ratio question we just talked about is not very uncommon either, because that really demonstrates whether or not you know the difference. Another thing that needs to be stated is we did this with water, and I will keep using water because it is the most common fluid you will be dealing with in the course. However, if someone, again, wanted to see if you knew what you were doing, the very first thing they would do is change it to a different fluid. They could have it be oil or even mercury, which is an extremely dense fluid at room temperature. Atmospheric pressure is always assumed to be this value. Technically, if they wanted to, they could change the surface of the planet and make something up, but I have literally never seen that done. So the density of the fluid is likely to change. Atmospheric pressure, not so much. And this height is height from where your object is to the surface. I keep exchanging it with the word depth on purpose because they are essentially the same thing. And again, this pressure is exerted in all directions. Lastly, the whole thing about the pressure being greater at greater depth, even for the same object, is going to be very important for our next video. Because if the forces per unit area are greater at the bottom part of the object relative to the top of the object, therefore you technically have an unbalanced pressure. But we will go into detail on that on the next video. Alright, so today we talked about gauge pressure, absolute pressure, what they are, how to find them, and a basic overview of how they may come into play. I think I will end it here. Have a good day. This is Mr. M, signing off.